Hi, in this problem, I want to talk about how to find the limit and prove the result of the following. The limit as n goes to infinity of 2 plus 1 over n. Using our techniques from calculus, we recall that when n goes to infinity, quantities like 1 over n trend towards 0. So the result here is going to be 2. Now we get to the more challenging part, and this is the part that our real analysis course focuses on. We want to prove the result. So the claim is that the limit as n goes to infinity of 2 plus 1 over n equals 2. And the proof for these problems, it often starts in a very unoriginal format. We usually start our proofs with let epsilon greater than 0 be given. All right, so we're going to start off. Let epsilon greater than 0 be given. Pick n, capital N, a natural number where capital N equals something. We don't know. And a lot of times I see students getting stuck here. And what we need to do is kind of reverse engineer that capital N. All right, so let's look at what we need to happen. Let's write down what we want to happen, and then we'll come back to our proof. So for that, I'm going to go to a scratch paper area. What we need, by definition of the convergence of a sequence, what we need is we need a sub n minus L, the absolute value of that, to be less than epsilon. Substituting in the values for our sequence and our limit, we get 2 plus 1 over n minus 2 is less than epsilon. That simplifies to the absolute value of 1 over n less than epsilon. Okay, so far so good. I'm just plugging things in and simplifying. At this point, we can drop those absolute value signs because n is a natural number, it's never going to be negative. Let me make this a different color. So at this point, we are after our n. We want to know what kind of n do we need to work with. So if I multiply both sides here by n, and then I divide by epsilon, remember epsilon is strictly greater than 0, so there's no trouble dividing by it. It's never going to be equal to 0. We're getting a very good sense of what n needs to look like. We need little n greater than 1 over epsilon. In other words, what this says is as long as our little n values are bigger than this 1 over epsilon quantity, this definition of a sequence, convergent sequence, it'll work, all right? And in the proof, the little n is always strictly greater than the big N. Bottom line, we need to set capital N equal to 1 over epsilon. All right, let me show you how that will work. And now let's work with it in the problem. And I'll get rid of that highlighting. Okay, so far, let us epsilon greater than 0 be given. We're going to pick a natural number n where n is equal to 1 over epsilon. All right, so now let's tell the reader that they should observe that, here we go, the absolute value of 2 plus 1 over n minus 2 absolute value simplifies to simply 1 over n. And that simplifies to 1 over n. Let me get in back in math mode. And I'm going to make a note here for all little n in the set of natural numbers. Okay, and that is going to be strictly less than 1 over n for all little n greater than capital N. How do we know that's true? Let's just double check. If we divide both sides by n and little n, on the left-hand side we get 1 over capital N, on the right-hand side 1 over little n. So yes, indeed, 1 over little n is less than 1 over capital N. Okay, so we can put that in by choice of capital N because n equals 1 over epsilon implies that epsilon equals 1 over n. Okay. You could even gray that out. That was a bit of overkill. We really didn't need to say that, but sometimes the first time through these proofs, it's really good to convince yourself everything is on the right track. All right, so what have we shown? Let's wrap it up. Let's make a conclusion. So by definition of the convergence of a sequence, the limit as n goes to infinity of 2 plus 1 over n equals 2. Okay.